The intent of this video is to unpack the tactics and usage of aircraft-deployed Sonobuoy sensors adopted for detecting German U-boats in World War II. This is a Part 12 video of the channel's Bombers vs. Submarines Battle of the Atlantic series. Aircraft sunk more U-boats than surface ships in World War II, as shown in this chart outlining the monthly worldwide causes of submarine sinkings from a declassified 1946 Chief of the Naval Operations document titled Antisubmarine Warfare in World War II. All of the images in this video are declassified. Aircraft were responsible for 5.1 U-boats sunk per month, whereas ships were responsible for 5.0 U-boats sunk per month. As discussed in previous videos, an aircraft better attack a submarine quickly, as once the U-boat submerged beyond 15 seconds, the likelihood of a successful depth bomb attack is nil. The U-boat's greatest anti-aircraft defense is a quick crash dive. Once submerged, a submarine is well insulated from the air, as discussed in this April 1945 U.S. Air Force Historical Studies report titled The Anti-Submarine Command. The magnetic anomaly detector and airdrop Sonobuoy sensors were developed to allow aircraft to detect submerged U-boats. The sensors can be used to search and track submarines. Usage and combat effectiveness of the MAD sensor, coupled with the retro rockets, was covered in the channel's Part 9 video. The UBoat War was a battle of gadgets as discussed in this May 1946 Bureau of the Navy Personnel Bulletin. The Allies were victorious over the Axis U-boats due to the ability to find and track U-boats with sonar, sonobuoys, radar, and HFDUF. The battle was a constant seesaw between measure and countermeasure. Saltwater provides excellent concealment for U-boats, as discussed in this 1951 Office of the Scientific Research and Development report titled Subsurface Warfare, The History of Division 6. It is almost opaque to all forms of radio, radar, infrared, ultraviolet waves, and light. The only practical means of U-boat detection is tracking its sound. A submerged U-boat has a weakness that can be exploited. Under normal conditions, it must keep moving to maintain equilibrium. The U-boat will produce sounds to keep moving. Sonobuoy sensors can detect these sounds. Sonobuoys were introduced to aircraft crews in the new technical development section of the January 1943 Anti-Submarine Command Monthly Intelligence Report. An underwater ear would be helpful in tracking and locating U-boats. Once a U-boat has submerged, it is well insulated from aircraft visual and radar sensors. A tethered aircraft-deployed microphone is not practical. A solution is to have a deployed underwater microphone that is relaying the sounds back to the aircraft. The Navy provided training devices to assist sonobuoy operators in detecting U-boats, like shown in this image from a January 1945 Naval Aviation Bulletin. Let's listen to various underwater sounds from this training aid.
Sonobuoy effectively, you must be able to detect the sounds produced by a submarine. This isn't always easy, since modern submarines are designed to make very little noise. Furthermore, you must pick out the sub-signals from the background noise which is heard over any underwater listening system. This background noise is produced by water surging around the hydrophone, by waves breaking on the surface, and by similar water disturbances. Water noise has no definite pitch or rhythm. Over the expendable radio sonobuoy, it sounds like this. The sounds from a submarine, and these are the sounds in which you are especially interested, may be caused by the propellers, by the main driving machinery, and to a lesser degree by operation of auxiliary equipment. Listen first to the sound of a submarine's propellers. Note that these propeller sounds have a definite rhythm and can be easily counted. Now you'll hear the whine of the driving machinery. The operation of auxiliary equipment aboard a sub produces certain characteristic sounds. In the next example, you will hear the intermittent sounds produced by power operation of the bow and stern planes. Often you will hear machinery sounds and propeller beats together, as in the following example.
The Sonobuoy's original design criteria include that it must be small, easily stowed, quickly launched, and light. It must also be rugged, take the impact with the sea, waterproof, acoustically sensitive, transmit clearly, and be expendable. The Sonobuoy developed had a battery life of 4 hours, was 46 inches in length, and had a parachute to slow its water entry speed. It is 4.5 inches in diameter, includes a transmit antenna, and an underwater cable hydrophone dangling 20 feet below the surface. The unit weighs 15 pounds. The Sonobuoy's aircraft receiver can tune into one of 6 FM available channels. Each channel is color-coded. Sonobuoys can be used to determine if a MAD contact is a submarine or wreck. Strategically placed sonobuoys can tell the status of a U-boat if the submarine is running away or standing by. Sonobuoys can also narrow the U-boat's lost contact area of interest. Special training is required for an aircraft sonobuoy operator. Let's listen to various underwater propeller sounds.
These sounds are from a submarine's propellers. As the propellers turn rapidly, they create small, momentary cavities in the water. This effect is called cavitation. When the water rushes back into the cavities, it produces the sounds recognized as propeller beats. Cavitation depends mainly upon the speed and depth of the submarine. For example, an American fleet-type submarine running at periscope depth produces cavitation at speeds of 3.5 to 4 knots and above. When its speed falls below 3.5 knots, cavitation is usually absent and you hear only machinery sounds. Here is a sub of this type at a speed of 3 knots, periscope depth. Now the submarine speeds up to 6 knots. It is still at periscope depth. At this speed, cavitation is present and you can easily hear the beat of the propellers. Cavitation also depends on the depth of the submarine. As the depth becomes greater, cavitation decreases. In the next example, you will hear the same sub at the same speed, but at 250 feet. At this depth, a speed of 6 knots is too slow to produce cavitation. Consequently, you hear no propeller beats. If the sub stays at 250 feet but speeds up, cavitation will begin at about 6.5 knots. At 8 knots, the propeller beats will be clearly audible.
The image on the left shows the relationship between the U-boat sound emission, Sonobuoy's underwater hydrophone, Sonobuoy transmission of the sound, and the aircraft radio operator listening and processing the sound. The image on the right shows the Sonobuoy aircraft operator selecting the sonobuoy to listen to by rotating the buoy selection knob to the appropriate color-coded tuning window. The Sonobuoy adopted the ANCRT-1 or -1A is shown in this cross-section component labeled image. They can detect underwater sounds of U-boats. The buoys are preset to one of 6 frequencies. They are color-coded based on frequency. At water contact, the hydrophone drops 24 feet below the surface. An aircraft can receive a sonobuoy signal from 5 to 10 miles from an altitude of 300 feet and 30 to 40 miles from an altitude of 5,000 feet. The antenna is 39 inches in length when deployed. This image shows the various Sonobuoy aircraft support components, including the sound receiver, power supply, and antenna coupler from an August 1943 Radar Research and Development Subcommittee document titled U.S. Radar. A crew member releases a sonobuoy. The parachute slows the sonobuoy's water entry speed. The sonobuoy transmits the underwater sounds to the aircraft. The sonobuoy components are shown in this picture. The AN CRT-1 sonobuoys are considered a passive, omnidirectional hydrophone type, as discussed in this 2019 Acoustical Society of America Sonobuoy article. The buoys are passive since they are strictly a listening sensor. The hydrophone is omnidirectional as it picks up underwater sounds from all directions. Sonobuoys can be deployed for other reasons other than submarine detection, as shown in this list compiled from the January 1945 U.S. Fleet Anti-Submarine and Escort of Convoy Instructions document. It is critical that the aircraft maintain orientation to the sonobuoy pattern laid. Drop all sonobuoys, usually 5, in a predefined pattern. Don't deviate from this pattern based on mid-drop detections. All crew members need to be trained in sonobuoy usage. Adopt gambit search techniques if alone. Orbit away from the contact location and listen for surfacing sub noises. Gambit searches were covered in the channel's Part 8 video. A gambit search sonobuoy pattern is different than a lost contact sonobuoy pattern. Let's listen to various underwater propeller sounds.
Some submarines are naturally noisier than others, and every submarine makes more noise as it increases speed. Everything else being equal, a noisy sub can be detected at a greater distance than a quiet one. Because of these variable factors, no definite range of detection can be given. Under good conditions, the expendable buoy will detect a submarine at a range of several thousand yards. When the sub is close to the buoy, the sounds will be strong. As the sub moves farther away, the signals become weaker, until finally they are completely lost in the background water noise. The submarine is at periscope depth and at a speed of 6 knots. First, the sub at a range of approximately 200 yards. And now at a range of 1,000 yards. Although the propeller beats are weaker, you can still hear them through the water noise if you listen closely. Let's listen once again to the sub at 200 yards. This difference in volume is useful when you are trying to locate a submarine. For instance, suppose you are listening over 2 buoys of a pattern. You tune in on one and you hear then you tune to the other. The sounds from the first buoy were weak. The sounds from the second buoy were strong. Evidently, the sub is closer to the second buoy than it is to the first. Comparative listening is used in this manner with all the buoys of a pattern, so that you may determine the approximate location of the submarine.
This chart outlines the drop pattern for a typical submerged U-boat. Set the directional gyro to 0, or fly at a magnetic north direction. Drop the first sonobuoy 1,500 yards from the U-boat submergence point. 1,500 yards equates to 0.85 miles. The first sonobuoy dropped is at the red frequency. The second sonobuoy is dropped over the point of submergence. The second sonobuoy is the purple frequency. The third sonobuoy is dropped 1,500 yards past the point of submergence. The third buoy is at the orange frequency. Fly a 270-degree left turn. Drop the fourth sonobuoy 1,500 yards from the U-boat's point of submergence. The fourth sonobuoy is at the yellow frequency. The fifth sonobuoy is dropped 1,500 yards past the point of submergence. The fifth sonobuoy is at the blue frequency. The green frequency is a backup sonobuoy. If two sonobuoys of the same color are deployed, locate them as far apart as possible. This chart indicates the approximate sonobuoy U-boat detection range. The x-axis is a range in yards from 2 to 10,000. Note that 10,000 yards equates to 5.7 miles. The y-axis is the U-boat's depth and speed. The DE implies a surfaced U-boat under diesel engine power. The family of curves in the body of the chart represent the sea state. Given this chart, a sonobuoy operator should be able to detect a U-boat traveling at a speed of 4 knots at a depth of 250 feet in a sea state of 1 if the U-boat is traveling within 1,500 yards from the sonobuoy. At periscope depth, detection will occur if the U-boat is traveling within 3,500 yards from the sonobuoy. Let's tie together the material shown with an example.
Suppose that a submarine has been reported in a certain area. Your plane is sent out to investigate. You drop a pattern of 3 buoys. Lay out the pattern on your paper. Purple in the center, orange at north, and blue at east. Assume that you drop all 3 buoys and then begin listening. First you tune to purple. You tune to orange. You tune to blue. You turn back to purple. Orange. Blue. Study your buoy diagram. Indicate the location of the submarine with the letter S. Let's review the problem. On purple frequency, you heard weak propeller sounds. On blue, you heard strong propeller sounds. On the orange buoy, you heard only water noise. Therefore, the submarine is probably quite a distance from orange and between purple and blue. Since the signal came in strong over blue, the sub is probably quite close to the blue buoy.
For the next sound clip, you will need pencil and paper. Be aware that the sub is moving and that the buoy sound may change from first pass to second pass. A quick way to pause a YouTube clip is just to hit the space bar. I'll show you the answer to this test in the channel's next video.
This time, assume that you have dropped a pattern of 5 buoys, and you are now ready to tune from one buoy to another. Draw a pattern on your paper. Purple in the center, orange at north, blue at east, red at south, and yellow at west. As you listen to each frequency, write down on your pattern the signal heard and the relative strength of the signal. You tune to purple. And next to orange. Blue. Red. Yellow. You again tune to purple. Orange. Blue. Mark the sub's location with the letter S. Comment briefly on the sounds you heard. Show where more buoys might be dropped to good advantage.
So how effective were sonobuoys in detecting U-boats? Sonobuoys were given low priority in the pecking order of anti-submarine developments, as defined in this Combat Studies Institute report titled History of the Anti-Submarine Measures Division of the 10th Fleet. The sonobuoys were given a ranking priority of 12 out of 12 anti-submarine projects. In hindsight, the sonobuoy project was ranked too low. Sonobuoys were used more frequently at the end of the war to detect the noisy German-equipped schnorkels, as discussed in this 1978 report titled Sea-Based Airborne Anti-Submarine Warfare, 1940 to 1977. Analysis indicated that in over 50% of cases where sonobuoys were deployed, following the loss of a visual contact, a sonobuoy detection was obtained. If you've enjoyed this video, please let me know in the comment section. Also considering liking the video and subscribing to the channel World War II U.S. Bombers.